Welcome back. We're on 9-4, quadratics and projectiles. This is the fun part of quadratics, I think. A little bit you should know here, the vocabulary about what is the force of gravity. What does it mean to have initial upward velocity, and what is initial height? How that relates to the equations. We have two forms of the equation we're going to talk about. The first one has to do with the equations for the paths of a projectile, and this is really in the activity. The activity you're going to need to do in class, come and see me. I've got some sheets of paper you can put up. You'll need a partner or two, but you'll be able to create your graph. If you want to take it further, we can get you the microwave motion detectors out of the science lab, and you can use those to create data and a plot of a projectile motion and get your own path information from that, or time. So that's the equations for paths, and then we have the equations for the height of a projectile over time. What's interesting is both of these are parabolas, but in one case the parabola actually describes the path of the object. That's in this path of a projectile. For the height parabola, it simply shows height versus time, and even though it is a parabola, it is not the path of the projectile. We'll see this as we go through it. Again, see me about activity 1, get you set up either old school or with some new technology. We'll help you out. Okay, when a projectile is launched, several factors determine its height above the ground at various times: the force of gravity, the initial upward velocity, and the initial height. Now, if you look at figure 1, years ago the belief was that when something was launched, that when it came back down, it came down much more directly or more quickly than it went up in the first place. And so that would be the figure 1 situation. It goes up and it just comes right down. What we know, and this is the work of Newton, Galileo, and Tartaglia, that in fact the path is a parabola. Newton is the one that tied the reasons for the parabola to the force of gravity, but that is why it follows that path. Gravity we have in two different units, and you'll want to pay attention to which unit it's in. In the case of 16, the force of gravity in our customary system is 32 feet per second squared. You'll notice that 16 is half of that, and that's a feet equation. So that's 16 feet per second squared times time squared leaves you with feet, right? The units work out. So this is customary units. In our metric system, it's 9.8 meters per second squared. And you can guess what that would look like. Since this is 9.8, this was 32 and we got 16, this is 9.8. So the unit we would see would be 4.9. That's meters per second squared, and that would be times our times square unit. So if you see 4.9 or a 16t squared, that gives you an indication of what kind of units you're dealing with. 16.9 is customary, feet is the unit of length. 4.9 is metric, meters are the unit of length. We have a general formula for the height. We have a negative 16t squared, negative because gravity is pulling downward. Velocity, v is the velocity, that's feet per second, and it's positive, so it's indicating an upward velocity. And finally, we have an initial height. How high was the object when it started? If I was holding it and throwing something, well, I'm probably throwing it from over 5 feet off of the ground. So my initial height would be different. For a football player reaching back to throw over the top of their head, it may be 7 feet off of the ground at the release point for a football. So we got to pay attention to that S value. I have a simulator. It is at this website. You might want to go to it to take a look, but I'm going to go ahead and pull it up now and show you what it looks like. It's kind of fun. Gives you a chance to kind of look at various objects being flung around and see how it's influenced by various factors. So here is our simulator. We have our cannon. We can change its angle of launch. We have a tape measure should we want to measure distances. You'll notice that it's in meters, so we are in the metric system. And we can launch various things. We have our angle, our initial speed, the mass of our object, and the diameter of the object. Without air resistance, the diameter won't make any difference. Here, I'll show you. So I've launched my object, and it's 0.1, and now I'm going to make it 20, and I'm going to launch my object, and it made no difference. So the diameter was unaffected by it. So if I have 0.1 and I include air resistance, I'm going to need to erase all this, and I fire, I now see, yeah, it went about where it was before. I'm not going to go to 20 because that was just too huge. How about 10 with air resistance? And what happens? Well, it didn't go very far at all because of the drag. Let's see if we can get it to travel. How about 2? 1? Okay, so we can see that air resistance does have an impact. For our purposes, it's not really useful. You can change mass, initial speed, angles. You can change what you launch. We have a tank shell, a golf ball, pumpkin, and there's all kinds of different things in here, human, what else? There's other stuff. So have fun with it. It just, you can see that this is a parabola. If we get air resistance in there, it does have an impact on the path. It's not strictly a gravity situation, but it just, this is a little bit of fun for you to look at and have some fun with. Okay, well, let's get to work. Example 1, a ball is thrown from an initial height of 10 feet with an initial velocity of 64 feet per second. Write an equation describing the height h in feet of the ball after t seconds. How high will the ball be after 3 seconds? And what is the maximum height of the ball? Just to elucidate this idea of path versus height, if we have a ball that is pretty much just thrown straight up and comes straight down, it'll follow a parabolic path that'll look something like this path looks like. The height of the ball versus time will also be a parabola, but not the same as the path. It'll go up at a certain time and it'll come down taking the same amount of time, and it'll return, well, it'll come back to wherever it lands. If it started at a greater height, it may not land at the same height it started from. So I just put this up here. I wanted to try to make sure that was clear. Let's go ahead and write our equation. It's in feet, so if it's in feet, we're going to use a negative 16 t squared plus 64 feet per second, 64 times t, and the initial height was 10, and all of this equals h. So we have h equals, a negative 16t squared plus 64t plus 10. We've written our equation. How high will the ball be after 3 seconds? Okay, well that is asking us to take for t equals 3, so a negative 16 times 3 squared plus 64 times 3 plus 10. We're going to go ahead and solve this equation and find that h equals 58 feet. Okay, now here's a question for you, which is, what is the maximum height of the ball? And that's easily solved using a graphing calculator. So let's pull one up and take a look at it. We want to graph, and our function is the equation we just wrote, so a negative 16 times, now because this is f of x, I need to use x instead of t. I know that it might be a little confusing, but your calculator wants what it wants. Plus 64 times x plus 10. Okay, we've got our equation. I'm going to go ahead and enter it. I think the window is going to be horrid. Indeed it is. So I need to narrow this down. This is 1, 2, 3, 4. So I'm going to make this from 0 to 5 for the x window. And I can see already I have a measurement at 58 feet after 3 seconds, so I'm going to be way beyond 6.67. So go to Menu, Window, Settings. I'm going to make my x minimum just 0. My x max, make that 5. Y minimum, also make this 0. And Y max, I don't know, we got to pick something. I know it's over 58 feet, so how about 90? We'll pick 90 feet. And if I don't get it right, I can adjust it, right? Oh, okay. So I've got a graph now, and that graph shows me my parabola. We go into Menu, and in Menu, we have an Analyze Graph function. That's number 6. I want the maximum because I've asked for the maximum. Analyze graph, maximum. Now it's looking for the boundaries on it. It could be that I have some complex graph that has many maximums, so it gives me an opportunity to select where I want the maximum from. So there's my lower bound, here's my upper bound, and I'm given my maximum point of 274. So I know then that the maximum height of the ball for this situation is 74 feet. Now another interesting question that we could answer while we're in here is, we're at 58 feet after 3 seconds. Well, the ball goes up and the ball comes down. Do we hit 58 feet at some other time? And we must, because at 2 seconds, we're at 74 feet. At 3 seconds, you're at 58 feet. So that must mean at 1 second less, at 1 second, you're also at 58 feet. Let's verify that and see. Analyze graph. Oh, I need to put in another function. And this is just simply 58. I want a horizontal line at 58, and there I've got my horizontal line. I go back to Menu, Analyze Graph, Intersection, and again it's looking for boundaries. I got my lower bound, my upper bound. I see I have an intersection at 158, which is what we predicted based on symmetry. Let's just double check and make sure our 3 was correct. Go to intersection, lower bound, upper bound, and at 358. So I have verified my results that at 3 seconds I'm at 58 feet. I also can show that I would also be at 58 feet at 1 second, and symmetry holds in that at 2 seconds I'm at maximum, which is my vertex, so my x values must be evenly spaced beyond that. So if I go 1 second more or 1 second less, I will have the same y value. Okay, let's pull this down out of the way and get on to our next example. This is your guided example in the textbook. It is on page 547. Object is dropped from an initial height of 90 meters. Write a formula describing the height of the object in meters after t seconds. After how many seconds does the object hit the ground, and what is the maximum height of the object? Okay, units are in meters, so we're going to use a negative 4.9 times t squared plus the initial velocity times t plus s. We're going to substitute 90 for s. The initial velocity was 0. It was dropped. So it was not given any initial velocity. It was simply let go. So our initial velocity is 0. Our height, initial height was 90 meters. We started at 90 meters and dropped the ball. So this reduces to 90 meters plus a negative 4.9 times t squared. So the value of t corresponding to h equals 0, how many seconds does the object hit the ground? So when the equation is set equal to 0, then that means a negative 4.9 times t squared plus 90 meters equals 0. So 4.9 times t squared equals 90 meters. I'm going to divide both sides by 4.9 and get that t squared is approximately 18.37, and that's seconds squared. T is positive. It measures time after launch, so we are only concerned with the quadrant 1 solutions. We don't have to concern ourselves with the negative square root. We take the square root of 18.37 and we get it's approximately 4.3, and that's seconds. So this is when h is equal to 0. You should find the object hits the ground in about 4.3 seconds. Now the graph is showing it right, and the graph shows that the object is farthest from the ground when it is launched, because there was no upward velocity. So that means its maximum height of the object is 90 meters. And we could have known this just simply because initial velocity was 0, that the height it started at was the maximum height. There was no impetus, no force to cause it to go to a greater height. Okay, we good? All right, well, I'm going to move ahead to the next guided example. This is guided example 3 in your textbook. Suppose a ball is thrown upward with an initial velocity of 22 meters per second from an initial height of 2 meters. Write a formula for the height in meters of the ball after t seconds. Estimate when the ball is 20 meters high. Okay, because units are provided in meters, we're going to use a negative 4.9 times t squared plus v times t plus s. We're going to substitute 2 for s and 22 for v. So our formula is a negative 4.9 t squared plus 22 times t plus 2. Okay, the value of t corresponding to h equals 20 must be found. Graph the equation you found in part A on the window. 0 to 6 for x and 10 to 30 and draw a horizontal line to indicate 20 feet. Okay, and then use the intersect command. We did this a minute ago, didn't we? All right, so let's go back to our graphing calculator, and we'll get a new, I'm going to get a new window here. Add a graph. Okay, so in this window, I'm going to go ahead and put in my function, and this was a negative 4.9. Remember, we're going to have to use x times x squared plus 22 times x plus 2. Enter it. We've got to adjust our window. They gave us a window setting, right? So 0 to 6. And 10 to 30. Okay, so I've got a my parabola. I can see it pretty clearly. I'm going to go to menu, graph function, and what was the height I was after? This was the height was h equals 20, so I put in 20, enter it, and I now have my horizontal line. Go to menu, analyze graph, intersection, lower bound, upper bound. I have a 1.08 and 20. And I want to do that again. Analyze graph, intersection, and I have a solution to this is that the time for the height of 20 is 1.08 seconds and about 3.41 seconds. So one was 1.08, so we'll call that just 1.1, and the other one approximately 3.4. So we now have our information we need. We could have found out the maximum from this from the graph using the maximum command would give us a way to pick that up. We could determine it now by finding out the time. What time is halfway in between 3.4 and 1.1? And if we know that time, that would be the time of maximum height, because these are equidistant on either side of the vertex through which the line of symmetry falls. Okay, that's it for 9.4. Hope it was entertaining for you. Best of luck on the mastery quiz. Remember to pay attention on the graphing calculator to entering x as the calculator demands and not t as the equations are describing. So you just have to make that adjustment. I'll see you in class.